LABTECH Innovations.
Hello dear students, today we will discuss molecular orbital theory, which is a very important concept in chemistry because by using MOT any molecule can be represented easily and bond orders hybridization as well as magnetic property can be explained using molecular orbital theory. This theory also helps to write and to show the molecular electronic configuration of diatomic molecules. Let us start molecular orbital theory. Dear students, you are familiar with the valence bond theory, which describes the formation of covalent bonds by overlapping of half-filled atomic orbitals. This theory is successful to give satisfactory electronic description for a large number of molecules. In some cases, it gives to incorrect electronic descriptions. Therefore, another bonding description called molecular orbital theory has been introduced. It has been found that the molecular orbital theory gives more accurate description of electronic structure of molecules. The concept of an atomic concept of orbitals is introduced by quantum mechanics. The quantum mechanical wave equation is a different equation and its solution is called a wave function. The square of wave function gives a measure of probability of finding an electron within a certain region of space of an atom. It is nothing but an atomic orbital. Molecular orbital theory does not concentrate on individual atoms. It considers the molecules as a whole rather than an atom for the bonding. According to a molecular orbital theory, MOT is the property of a molecule similar to what an atomic orbital is to an atom. Hence, molecular orbital can be detected through a square of wave function that gives the probability of finding an electron within a certain region of space in a molecule. Like atomic orbitals, molecular orbitals have energy levels and definite shapes. They also contain maximum 2 electrons with opposite spins. MOT can explain by following 6 insights. See, these are the 6 insights which are number 1, that is the formation of molecular orbital, then conditions for combination of atomic orbitals, then the third approach is about types of molecular orbitals. It is 2 types, MO, AMO, BMO. The fourth is about energy levels and electronic configurations, and the fifth about the key ideas of molecular orbital theory. Molecular orbital description of simple diatomic molecules, that is the extract or abstract or aim or objective of the MOT. These 6 approaches makes MOT very interactive or very interesting. Say, formation of molecular orbitals. This is the example given here. So, according to molecular orbital theory, the formation of molecular orbitals from atomic orbital is expected in terms of linear combination of atomic orbitals. That is what? LCAO, linear combination of atomic orbitals. You can see here in this slide, it is visible how the linear combination of atomic orbitals is occurring here. Formation of molecular orbitals can be understood by considering the interference of electrons wave of combining atoms. Interference of electron wave can be constructive or can be destructive. That is, the wave can reinforce each other. The waves can reinforce each other and or cancels each other. So we can say that two atomic orbitals, if they cancels each other, they can reinforce each other. So we can say two atomic orbitals combines two ways to form molecular orbitals. This is one way of combining of molecular orbitals. These are the atomic orbitals. They are combining and they will give two MO molecular orbitals. Okay. So by addition of their wave functions, this is the addition of wave functions. And second one is about by subtraction of their wave function. This is what the subtraction of their wave function. Addition, addition of the atoms. Addition of the atomic orbitals wave functions results in the formation of molecular orbitals which is low in energy. So if there is addition, so the new MO is being formed here. This is the low in energy. Okay, while the subtraction, or we can say it is termed as BMO, bonding orbitals, which is low in energy, or terms of the bonding molecular orbital. In short, it is called as BMO. BMO. Subtraction of atomic orbitals or wave functions results in the formation of molecular orbitals with higher in energy. When there is subtraction, there is a formation of molecular orbitals which are higher in energy. They are called as anti-bonding molecular orbitals, which are high in energy, and they are called as anti-bonding molecular orbitals. You can see in this case AMO in short. BMO is a bonding molecular orbitals. AMO is a anti-bonding molecular orbitals. Now see in here, in bonding MO, in bonding molecular orbitals, the large electron density is observed between the nuclei of bonding atoms than the individual atomic orbitals. On the other hand, in the anti-bonding molecular orbitals, in this case here, in the anti-bonding orbitals, the electrons density is nearly zero between the nuclei of the atoms. So, placing electron in bonding orbital leads to formation of a covalent bond, while placing electron in anti-bonding orbitals makes the bond unstable. So here there is a BMO, here AMO. If electron is being placed here, it gives the formation of a bond, while if electron is placed here, going here, it gives a instability, or bond is not going to form. See, second condition is what? The second approach is about condition for the combination of atomic orbitals. So condition for the combination of atomic orbitals, in this what we learn, what point we can get, atomic orbitals can be combined linearly. They combine linearly, which gives more molecular orbitals only if following conditions are fulfilled. What are the following conditions? The combining atomic orbitals must have comparable energies. Number one point. So we can say 1s orbital of one atomic orbital. 1s orbital will always combine with the 1s always combine with the 1s atomic orbital of another atom, but not with the 2s. 1s will combine with the 1s. 1s will never combine with 2s, because energy of 2s is much higher than that of 1s. This is the number one point. See here you can see this, the energy level. Second point is the combining atomic orbitals must have the same symmetry along the molecular axis. Conventionally, z-axis is considered as taken as a internuclear axis. Z-axis considered as internuclear axis. So even if atomic orbitals have same energy but the symmetry is not same, they cannot combine. So condition is they should have same energy but symmetry should be there. For example, 2s orbital of an atom can combine with the 2pz orbital of another atom, and not with the 2px or 2py orbital of the atom, because the symmetries are not same. Pz is symmetrical along z-axis, while px is symmetrical along x-axis and py along z-axis, y-axis. The combining atomic orbitals must overlap to a maximum extent. Greater the overlapping is the greater is the electron density. If overlapping is greater while forming of molecular orbital, so the density of electron would be greater between the nuclei, and so stronger is the bond formed. So you see in the next slide, you can see here this 1s adding, and they will form bonding molecular orbitals. When these 1s they are undergoing subtraction, there is no formation of bond. So here in this slide, we can discuss the types of molecular orbitals which are formed when two atomic orbitals combining. So in diatomic molecules, because we are dealing with the diatomic molecules, molecular orbitals formed by a combination of atomic orbitals are of two types, that is sigma and pi. Sigma molecular orbitals and pi molecular orbitals, and they are anti-bonding also. According to this nomenclature, a sigma designated a molecular orbital which is symmetrical around the bond axis, and pi designates a molecular orbitals those are unsymmetrical. This is clear if we consider a linear combination of two atomic s orbitals and or two p orbitals. See this figure, we are taking two hydrogens, isolated hydrogens. Two hydrogen atoms are there. See, this is their energy of isolated hydrogen atoms. So when they are adding, they will form bonding MOs, you can see here, because they are going addition. When there is subtraction, they undergo means there is no formation of bond. This is called as a node. Node means the area where there is no electron density is present. Okay, the s orbitals are spherical, symmetric along x, y and z axis. Combination of two s orbitals centered on two nuclei of the two atoms, say hydrogen, led to a molecular orbital formation which are symmetrical along the bond axis. One of which is a bonding molecular orbital, we can say sigma bonding molecular orbitals. Another is what? Sigma star. So this is what? Sigma. This would be sigma. This would be sigma star. You can see here. This is sigma star. This is the sigma. Or we can sigma 1s, sigma star 1s. So this is sigma star bonding, sigma bonding, and that is sigma antibonding. If we consider Z to be internuclear axis, the linear combination of pz orbitals from two atoms can form sigma 2pz bonding and anti-bonding sigma star 2pz molecular orbitals. The px py orbitals are not symmetrical along the bond axis. They have a positive lobe above the axis and negative lobe below the axis. Hence, linear combination of such orbitals leads to the formation of molecular orbitals with the positive and negative lobes above and below the bond axis. These are designated as pi bonding and anti-bonding orbitals. The electron density in such pi orbitals is concentrated above and below the bond axis. The pi molecular orbitals has a node between the nuclei. In this case, see the energy level and electronic configuration. This is the most important slide of to explain the molecular orbital theory. We have seen earlier that on combination of two 1s orbitals, two molecular orbitals of sigma 1s, sigma star 1s are formed. Similarly, sigma star 1s, sigma 1s and sigma star 1s. Similarly, two 2s atomic orbitals will combine, will form sigma star, sigma 2s, sigma star 2s. Similarly, 2p orbitals on atom combine with the 2p orbitals and they will form the sigma 2pz, sigma star 2pz, and pi bond will form when px and py will combine, and they will give the pi px pi py and pi star px pi p star py. So you see here the example is given for diatomic molecules of second row elements except oxygen and fluorine. The bond energy order of these molecular orbitals is given here, and this order has to be followed. That is what he start from his sigma 1s is lower than sigma star 1s, lower than sigma 2s, which is lower than sigma star 2s, which is lower than pi 2px, and which is equal to pi 2py, and which is lower than pi, which is lower than sigma, which is lower than sigma 2pz and sigma 2pz, and which is lower than pi star 2py equal to pi star 2px, which is lower than the sigma star 2pz. This is the energy level and most important what we can say the slide of the molecular orbital concept. In this slide you can see for O2 and F2 molecules the order of energy is slightly different. You see different. So this one, see here, this was here in the previous case. Yeah, this now we have brought this down here and this gone up. Okay, there's only one change we have to do. So in this case you see 1s is a sigma 1s, then sigma star 1s, then sigma 2s, sigma star 2s, and sigma 2pz, then pi will start, pi px, pi py, and like that. The sequence of filling the molecular orbitals give electronic configuration of molecules. The electronic configuration of molecules provides the following information. So what information we can get? See, this is the for O2 and F2. See, what information we can collect from MOT? We can find out the stability of the molecules, magnetic nature of the molecules, then bond order of the molecules by using the formula bond order is equal to Nb minus Na, means electron in bonding molecular orbitals minus electron in anti-bonding molecular orbitals. Okay, so we can find out the how many bonds are present between the two atoms. Similarly, by using the MO diagram, one can find out the magnetic nature if single electron present or not. For example, O2 molecule which has two single electrons can also be find out by using the MO diagram. Okay, then what about the stability of molecules? If more electron present in the bonding molecular orbitals, then such molecules are more stable. If electrons going the anti-bonding molecular orbitals or AMO, BMO is lower in energy, AMO is high in energy. Electron should go where? It has to go to the BMO, not AMO. If it is going AMO, the molecule become unstable. Fine. So in the next slide, we'll see that from the key ideas. What are the key ideas we can extract from the MO? The key ideas of MO theory is MO is in molecular orbitals molecular orbitals in MO are similar to atomic orbitals. Of atomic molecular orbitals describes region of space in the molecules representing the probability of an electron. So molecular orbitals are formed by combining atomic orbitals of different atoms. The number of MOs found is equal to the number of AOs combined. Atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals AMO and BMO. MOs or molecular orbitals, those are low in energy. Then the starting atomic orbitals are bonding, they are called sigma, pi, and MO molecular orbitals, those are high in energy are anti-bonding molecular orbitals represented by star, sigma star, pi star. We have seen the last slide. The electrons are filled in molecular orbitals beginning with the lowest energy. Only 2 electrons occupy each molecular orbitals and they have opposite spins, that is their spins are paired. The bond order of the molecular or molecule can be calculated from the formula. We have seen that number of electrons in BMO minus number of electrons in AMO divided by 2. So, from by using the concept of molecular orbital theory, we can sort out this case. See here, you see what is this explanation is about the atomic orbitals of H2 molecule. You see here, we have shown atomic orbitals of hydrogens. Then you can see how they are combining, forming 2 MOs, BMOs and AMOs. 2 electrons are occupying the positions, and AMO is vacant. Only BMO electrons are present. From this, we can also find out the electronic configuration of H2 molecules. Its bond order is 1 because 2 minus 0 divided by 2 is nothing but 1. So, from this slide we can say H2 molecule can have the bond order 1. Okay, and it is diamagnetic. Why? Because electrons are paired, hence it is a diamagnetic. Similarly, if you go to the next molecule, there is a lithium molecule. In lithium molecule there are 3 electrons divided, see 2 plus 1 3, another lithium 2 plus 1 3. They are combining, see they are these two, one has formed 2 MOs, and so this 2 will form 2 MOs, total 4 MOs, and distribution of electron will take place according to energy level. You can see 2 2 2, 1 from this, 1 from this, 1 from this, and 1 from this, and it's like this. And you see in 2s there is no electron in the AMO, anti-bonding. Therefore, by putting the formula, bond order for lithium molecule is 1, and it is again diamagnetic because there is no single electron. Now see here N2 molecules. So N2 molecules energy diagram is like this. You observe this diagram and we will find that in MOs there are no single electrons, therefore nitrogen is diamagnetic, not paramagnetic. Bond order, how we can find out bond order? Bond order of N2 is, what is the bond order? You forget, you calculate from this 6 are there, 6 by 3 nothing but the 6 by 2 nothing but 2. This is the oxygen molecule, O2 molecule. You see here how O2 is there. O2, you see, look at this case, there are 2 single electrons here. So these 2 single electrons means O2 molecule is paramagnetic in nature because of presence of single electrons. However, it was not explained by the VBT. If you go to the F2 molecule, F2 molecules is again diamagnetic. This is the MO diagram. Bond order can be calculated by 1. By drawing such MO, one can easily find out the bond order and diamagnetic nature and the electronic configuration of molecules. So we can apply this theory, okay, to solve many questions which were asked in previous exams and also for future exams. So thank you. Post your questions, queries. I hope this is a video will be helpful for you all. Thank you. Thank you very much.